Welcome back, everyone. So we've talked about quantization and what that does, but there's also called something double quantization, okay? And before we look at the diagram, I'm going to try to explain it, okay? So remember, quantization compresses neural network weights from 32-bit floats to smaller floats like 4-bit integers to save memory. But you need scaling factors, which are floats, to convert back to usable weights during our process, whatever we're doing, inference or training. And double quantization goes even further. It also compresses those scaling factors from floats to integers. But to turn those compressed scale factors back into usable floats, you need new scaling factors. These are the metascales, okay? So basically, it's like compressing the compression parameters, okay? And you still need some float parameters, and these metascales must stay as floats, but you need far fewer of them. So one metascale per large block of thousands of weights instead of one scale per a small group of, for example, 128 weights. So the process is you take the train model, you quantize the weights, you quantize the scaling factors, you save everything, okay, which is the quantized weights, the quantized scales, the metascales, and you save the metascales as floats. And during the time you need it, you reconstruct weights by first turning the compressed scales back into usable scales using the metascales, then using those reconstructed scales to dequantize the actual weights. And you're like, why does this matter? Well, it gets you extra memory savings, approximately 10 to 20% more compression on top of regular quantization. So it's crucial for running large models on limited hardware, okay? And the key insight is you can't eliminate all float parameters. You need some to bootstrap the reconstruction process, but this approach lets you use far fewer, okay? So now back to our process. Remember, for example, let's say OpenAI trains a model. That's this blue over here in the top left. Then they, when they want to save the model, they quantize the weights into 4-bit integers, but they also quantize the scales. For example, those are 8-bit integers, okay? So what gets saved? You have the quantized weights, the quantized scales, plus the metascales, okay? And now this compressed model can be distributed and used. So the metascales are the only ones that remain true floating point. For example, floating point 32, FP32 here. Because using these metascales, you can basically reconstruct the scales that were used to quantize the original weights, okay? So it's like the matrix. You compress the compression. So then you have the usage phase. You dequantize the scales using the metascales, right? Remember, the metascales are still in floating point 32, and so you dequantize the scales. Then you dequantize the weights using the reconstructed scales, and now you're ready for the computation. So here is the two-step reconstruction, metascales to scales, and then weights. Now, when do we dequantize? Well, we dequantize base weights for gradient computation, for fine-tuning, or for inference. You dequantize weights for final predictions, okay? So I know this is tough, but I really hope that I tried to explain it in a way that makes sense, because we're going to be using double quantization, okay? This is a production-ready project, so we want to make sure that we enable all possible optimization techniques that we can use. If you have any questions, please let me know. And otherwise, we're going to be back in SageMaker where we continue writing our script.